The Siddhanta Isakut Iroma Letter 1E47I, or Crown of Treatises, completed in the year 1154 by Bhaskara II, known reverentially as Bhaskaracharya, constitutes a watershed in the history of Indian mathematics and astronomy. It is a work of synthesis and profound originality, a four-part compendium that encapsulates the state of quantitative knowledge while simultaneously advancing it with powerful new concepts and algorithms. This essay undertakes a direct and systematic evaluation of the core claims, methods, and conceptual frameworks presented within each of the 4 books of this monumental work. The analysis will proceed sequentially through the Lilavati, the Bhāskara Macron JAGA Letter 1E47ITA, the GRAHAGA Letter 1E47ITA, and the Goladier, assessing the internal logic, the methodological rigor, and the intellectual assertions made by Bhaskara, thereby constructing a detailed portrait of his intellectual achievement, as articulated in his own text. The aim is to illuminate the specific architecture of his reasoning, moving beyond general praise to a focused critique of the treatise on its own terms, revealing the precise nature of its contribution to the scientific traditions of its epoch and beyond. Section 1. The Pedagogical Framework of Arithmetic in the Lilavati. The Lilavati, the first book of the Siddhanta Isakut Iroma Letter 1E47I, presents itself as a comprehensive treatise on arithmetic, or PA Macron Letter 1E60I Macron J Letter 1E47ITA. Its primary internal claim is one of pedagogical efficacy and completeness. The text is structured as a series of lessons delivered by a teacher to a young woman, the eponymous Lilavati, a narrative device that immediately frames the work's contents as accessible and engaging. The evaluation of this claim hinges on the clarity of its definitions, the logical progression of its topics, and the illustrative power of its examples. The book commences with foundational concepts, units of measure for weight, money, and length, establishing a practical basis for the calculations that follow. It then advances to the 8 fundamental operations of arithmetic, which include the standard for as well as squaring, cubing, and the extraction of their respective roots. Bhaskara's exposition of these methods is exceptionally clear, providing step-by-step instructions. A signal claim within this section is the treatment of zero. Bhaskara defines the result of a number added to or subtracted from zero. He explicitly states that a quantity divided by zero results in a fraction, with a zero denominator, a quantity he terms kahara. He characterizes this quantity as infinite and unchangeable, stating that nothing added to or subtracted from it alters its value. This is a profound conceptual claim, positing a specific mathematical identity for infinity as the result of a defined operation. The internal logic is consistent. He treats this kahara as a new type of number with its own properties, a significant step in formalizing the behavior of infinities within an arithmetical system. The evidence for the pedagogical claim is found in the famous poetic problems that populate the text. For instance, a problem describes a swarm of bees, a fraction of which alight on one flower, another fraction on another, with a single remaining bee hovering in her. The student is tasked with determining the total number of bees. These problems function as sophisticated mnemonic devices, embedding complex multi-step calculations within memorable narratives that require the application of fractions, linear equations, and the rule of 3, or Trerasiga, a cornerstone of Indian commercial mathematics. The validity of these problems as teaching tools is high, as they demand both procedural competence and conceptual understanding to deconstruct the narrative and formulate a solvable equation. The Lilavati further extends its claims to mensuration, providing formulas for the areas of triangles and quadrilaterals, and the volumes of spheres and excavations. His formula for the area of a psychic quadrilateral is precise. His approximation for the volume of a sphere is also presented with clarity. One of the more subtle claims evaluated here is the implicit one of scope. The Lilavati purports to be a complete arithmetic, and its coverage of topics from basic operations to complex commercial problems, and geometric measurements makes a strong case for this. Its structure, moving from simple definitions to intricate, multi-stage problems, supports the assertion that it is a systematically designed curriculum for mathematical instruction, a claim well substantiated by the coherence and comprehensiveness of its contents. Section 2. The operational and algorithmic claims of the BA. I Macron J letter 1E47 ITA, the second book, the BI Macron JAGA letter 1E47 ITA, or Seed Mathematics, advances the treatise into the realm of algebra. Its central claim is the establishment of a systematic and powerful framework for symbolic manipulation and the solution of complex equations. The work's evaluation begins with Bhaskara's full-throated acceptance of negative numbers, which he terms letter 1E5 B letter 1E47A, or debt, and positive numbers, dana, or wealth. He establishes a complete set of operational rules for these numbers, stating definitively that the product of two positive or two negative numbers is positive, while the product of a positive and a negative number is negative. This claim formalizes a concept that previous mathematicians had approached with some hesitation. Bhaskara's methodology treats negative quantities as legitimate mathematical objects, equivalent in status to positive ones, a crucial step for the development of abstract algebra. He further extends this systematic approach to surds, or irrational numbers, providing rules for their addition, subtraction, multiplication, and division. The internal consistency of these rules demonstrates a sophisticated understanding of algebraic structure. A primary focus of the BI Macron JAGA letter 1E47 ITA is the solution of equations. Bhaskara presents a clear method for solving quadratic equations of the former times x squared plus b times x equals c, which is equivalent to the modern quadratic formula. He recognizes that a quadratic equation can have two roots and provides the logic for finding both. A significant claim of completeness, he explains that one root may be inapplicable in the context of a physical problem, for instance, if it yields a negative length, showcasing an awareness of the distinction between abstract mathematical solutions and their real-world interpretations. The most powerful and original claim within the BI Macron JAJ letter 1E47 ITA, however, is the presentation of the Chakravarla, or Sylock method, for solving second-degree indeterminate equations of the type now known as Pell's equation. Specifically, he sought integer solutions for the variables of x and y in the equation n times x squared plus 1 equals y squared, where n is a non-square integer. Bhaskara's claim is that his Chakravarla method provides a general algorithm that will always yield a solution. The methodology is iterative. He begins with an initial guess, a, b, that satisfies the equation n times a squared plus k equals b squared for some integer k. He then introduces a new variable, m, and constructs a new solution based on the previous one using the identity derived from Brahmagupta's work, the bhavana. The critical step in the Chakravarla method is the clever choice of the variable m at each iteration to ensure the value of k gets progressively smaller, eventually reaching 1, which provides the solution to the original equation. The logical coherence of this algorithm is exceptional. Bhaskara demonstrates its power with challenging examples, such as solving 6 to 1 times x squared plus 1 equals y squared, producing the famously large integer solutions. An evaluation of this claim finds it to be entirely valid. The Chakravarla method is indeed a general and highly efficient algorithm, superior to the methods known in Europe until the work of Lagrange centuries later. Bhaskara's confidence in his method, which he presents without a formal, abstract proof but through its flawless execution on difficult problems, is a testament to his deep understanding of number theory. The BI Macron JAJA letter 1E47 ITA thus substantiates its claim to be a profound work of algebra, not only by systematizing existing knowledge but by offering novel, powerful algorithms for solving problems that were at the absolute frontier of mathematical Section 3. Evaluating the planetary models and computational accuracy of the GIA GIA letter 1E47I the GIA RAHA GIA letter 1E47ITA, or mathematics of the planets, forms the first part of the astronomical core of the treatise. Its fundamental claim is the presentation of a refined mathematical model for predicting the positions of the planets, the Sun, and the Moon, along with phenomena like eclipses and conjunctions. This evaluation focuses on the internal consistency of Bhaskara's model and the soundness of his computational techniques. The framework he employs is the established Indian geocentric model, which utilizes epicycles and eccentrics to explain the observed motions of celestial bodies. The claim here is one of refinement, not revolution. Bhaskara's contribution, as stated within the text, is the introduction of updated parameters and corrections, known as bija corrections, intended to improve the accuracy of predictions derived from older texts like the Surya Siddhanta. The evidence for this claim lies in the detailed tables and constants he provides. An assessment of these parameters against modern calculations reveals that they do, in many cases, lead to more accurate planetary longitudes for his epoch. He provides rules for calculating the mean and true positions of the planets, involving complex trigonometric calculations. A significant portion of the GRAHA letter 1E47ITA is dedicated to spherical trigonometry. One of its key claims is the presentation of an accurate method for computing sine values. Bhaskara presents a recursive formula for generating a table of sines, a method that allows for high precision. The formula is stated as the sine of the quantity A plus B equals the quantity sine of A times cosine of B plus cosine of A times sine of B. This is the standard angle addition formula for sine, and its explicit statement and use are central to the book's computational engine. He applies these trigonometric tools to solve problems of parallax, crucial for accurate eclipse prediction. His methodology for calculating solar and lunar eclipses is detailed and algorithmically sound within the geocentric paradigm. He provides clear steps for determining the time of an eclipse's onset, its duration, and its magnitude. The internal logic is robust, with each step of the calculation flowing from the geometric model of the Earth, Moon, and Sun and the shadow cast by the Earth or Moon. A particularly noteworthy claim within the GRAHA letter 1E47ITA pertains to the nature of the Earth itself. In a remarkable passage, Bhaskara describes what he calls the Earth's amacron KR letter 1E63 letter 1E60I execute AKTI, or power of attraction. He asserts that the Earth possesses a pull that draws objects towards it, explaining why objects on all sides of the spherical Earth do not fall off. This is a claim about a specific property of the Earth. An evaluation of this claim must be precise. Bhaskara is articulating a concept of terrestrial gravity. He describes a force directed towards the center of the planet that is inherent to the planet itself. The claim is localized. He does not generalize this power of attraction to all celestial bodies and does not propose an inverse square law. Consequently, while it is a profound insight into the nature of gravity, its assessment concludes that it is a qualitative, physical explanation for a terrestrial phenomenon rather than a universal mathematical law of gravitation. The GRAHA letter 1E47ITA successfully substantiates its claim as a state-of-the-art astronomical handbook for its time, providing internally consistent models and powerful computational tools, and refine the predictive accuracy of Indian astronomy. Section 4. The conceptual claims of celestial mechanics. In the Golodhyaya, the final book, the Golodhyaya, or Sphere chapter, delves deeper into the principles of spherical astronomy and the physical nature of the cosmos. Its claims are both computational and conceptual, seeking to provide a rational basis for the astronomical models presented earlier. The evaluation of this section must grapple with some of the most sophisticated ideas in the entire Siddhanta execute IROMA letter 1E47I. The book begins with a vigorous defense of the sphericity of the Earth and its suspension in space, Using observational arguments, it addresses objections, such as why the Earth does not fall, by invoking the aforementioned power of attraction. The Gaudier is rich with intricate applications of spherical trigonometry to solve problems related to time, the rising and setting of stars, and the orientation of the celestial sphere at different latitudes. Bhaskara's methods for converting between different coordinate systems, such as ecliptic and equatorial coordinates, are presented algorithmically and are mathematically sound. The internal logic of his geometric constructions on the celestial sphere is impeccable, demonstrating a complete mastery of the subject. The most advanced and debated claim of the Gaudier, and indeed of the entire work, appears in its section on planetary motion. Here, Bhaskara addresses the problem of determining a planet's instantaneous motion, or tachyligati. To do this, he introduces a concept that is strikingly similar to the fundamental idea of differential calculus. His claim is that one can determine the velocity of a planet at a specific moment in time. His methodology involves considering the planet's position at two infinitesimally close points in its orbit. He calculates the difference in longitude over a vanishingly small interval of time. In doing so, he arrives at a crucial result. He states that the difference between the sines of two nearby arcs is equal to the product of the cosine of the arc and the difference between the arcs. In modern notation, this is equivalent to stating that the derivative of the sine of x with respect to x is the cosine of x. This is a monumental conceptual leap. He has discovered a fundamental differential relationship for a trigonometric function. The evaluation of this claim requires careful nuance. Bhaskara presents this idea in the context of a specific astronomical problem. He uses it to create a formula for the instantaneous velocity in terms of the cosine of the planet's anomaly. He does not proceed to develop a generalized theory of differentiation or integration. His work lacks the formal concept of a limit. Therefore, the claim being evaluated is his assertion of a method to find instantaneous motion. This claim is valid. He successfully devises an operational method that works precisely because it rests upon a correct, albeit specific, differential insight. He grasped the core idea of representing a rate of change at an instant by examining an infinitesimal interval, a concept that forms the very heart of calculus. The wit of history lies in the fact that this profound idea was presented not as a new branch of mathematics but as a tool for a better astronomical calculation. The Gaudier thus stands as a testament to Bhaskara's ability to move from computational technique to deep conceptual inquiry, grounding his astronomical system in rational mechanics and, in the process, touching upon mathematical ideas that would only be fully developed in Europe 5 centuries later. In conclusion, a direct evaluation of the internal claims of the Siddhanta Execute I Roma Letter 1E47I reveals a work of extraordinary intellectual architecture. Its 4 books form a cohesive whole, moving from the foundational and pedagogical clarity of the Lilavati to the powerful algebraic algorithms of the Bhāskara Letter 1E47ITA, and from the refined predictive models of the Grāga Letter 1E47ITA to the profound conceptual mechanics of the Gaudier. The claims made within each section are, for the most part, substantiated by rigorous internal logic, consistent methodology, and demonstrable computational power. The Lilavati's assertion of being a complete and effective arithmetical curriculum is borne out by its systematic structure and illustrative problems. The Bhāskara Letter 1E47ITA's claim to have mastered complex equations is validated by the elegant and general Chakravala algorithm. The Grāga Letter 1E47ITA's claim of enhanced astronomical accuracy is supported by its updated parameters and sophisticated trigonometric framework, which also contains the seeds of a theory of terrestrial attraction. Finally, the Gaudier substantiates its claim to explain the mechanics of the heavens through its rigorous application of spherical geometry and its remarkable precalculus insight into instantaneous motion. Bhaskaracharya Treatise is a document of a mature scientific tradition, one where computational mastery was wedded to a persistent inquiry into the fundamental nature of number and the cosmos. The enduring significance of the Siddhanta Esakutai Roma letter 1 E47I lies in the sheer force of its reasoning, establishing a high water mark for mathematical and astronomical thought in the classical world and leaving a legacy of powerful ideas that continue to command intellectual respect.